Can we rule out internal variability as the main driver of recent tropical SST trends? Peter Hoybers and Rob Wills. So that should be really interesting. And there's also going to be a talk on the same subject at our sort of part of this general discussion at our May 27th event from Alexei Fedorov, who might say maybe it's a little bit of variability and forcing. So stay tuned for that. It should be a great event. But that's all the announcements. Now let's get to the good stuff. Our first speaker today is going to be Catherine Stauffer, who is a postdoctoral researcher at McGill University. Catherine, why don't you see if you can. And excellent. Okay, whenever you're ready, take it away, Catherine.
All right, thank you, Jonah. Today I'm going to be talking about kind of the end of my PhD and my time at FSU before I switched positions. So this community is very familiar that the cloud feedbacks are the largest source of uncertainty in the climate feedback parameter and subsequently estimates of climate sensitivity. And then those of us who study tropical deep convection are familiar that organized convection reduces cloud coverage, drives the mean state, and it more efficiently allows radiated cooling to space. So Allison and I were curious as to whether this convective self-aggregation phenomenon influences cloud feedbacks in the deep tropics, specifically using the framework of radiative-convective equilibrium. So we're going to be looking at this through three different properties of organized convection. The first is the existence of organized convection. So we're going to be looking at two different types of simulations, one which has organized convection and one which doesn't, and comparing the feedbacks between them. And then the second is the degree of organization. So different models and different domains organized to different degrees of organization within the domain. So we're going to be using a metric that quantifies how organized the state is and looking at the cloud feedbacks across that. There's a third property, how organization changes with warming. However, we didn't find any relationship, so I'm just going to be focusing on these first two here. So the data set I'm using is the Radiative-Convective Equilibrium Model Intercomparison project. It has over 30 models of various types, so global climate models and cloud resolving models. This talk focuses on the cloud resolving models, all consistently configured in RCE, which is the statistical balance between radiative cooling and convective heating. So it's an ideal framework for studying tropical convection in the deep, deep tropics. The simulations have uniform and fixed insolation and SST, no rotation or land. And then there are three simulations at three different SSTs. So we're going to be focusing on the cloud feedback between 295 Kelvin and 305 Kelvin. And then, of course, as I mentioned, we have our two domains. What we call RCE small doesn't have organized convection, while RCE large does have organized convection or aggregation of convection. And then because this is a statistical equilibrium, all values that I present are averaged over the last 25 days of the simulations. So in RCE, convection self-aggregation is the spontaneous organization of convection despite homogeneous boundary conditions. So for example, we don't have baroclinic forcing. And as I mentioned at the top, this affects domain mean climate variables, which has implications for potential changes in cloud feedbacks. So all right, this figure, we have an example of our RCE small versus our RCE large simulations. So the small is this square simulation. It's 100 by 100 kilometers. And you can see that the precipitable water, which is plotted, is spatially homogeneous everywhere, as opposed to our large domain simulations, which is 3,000 by 400 kilometers, where we have these alternating bands of dry subsidence and deep moist convection. So we use this metric called the index of organization, which compares nearest neighbor distance convective entities to a random distribution to quantify how organized these domains are. The important bit of this is that values over 0.5 indicate that the domain is organized. The closer you get to 1, the more organized. So in this plot right here, I showed the cloud resolving models in RCE-MIP, their IORG value, and you can see that we have this wide range from just barely organized, just above the 0.5, to highly organized up here. This particular model that we have these spatial plots for has a value of around 0.9, so it's one of our more organized simulations. And then the cloud feedback method that we use is the cloud rated kernel method by Mark Zlinka. And in the process to doing this cloud feedback method in RCE, we developed a cloud rated kernel specifically for RCE MIP, since we didn't think that the CMIP cloud rated kernels were appropriate for the climate state of RCE. And then we also, in the process of this, developed an offline ISCIP simulator because the RCMIP protocol did not call for instrument simulators to be run. So we had to figure out how to run this offline. And this paper right here, which was published in January or something, outlines that this was an appropriate use of the simulator with this offline data, despite the temporal frequency being different than when it's run online. And then we decompose this cloud feedback into contributions due to cloud amount, cloud top pressure, and cloud optical depth. So this third part is what I'm going to be focusing on for the rest of this talk. All right, so the next couple of slides, we're going to see a couple of panels that look like this. We have our different flux feedbacks in the colors and on the x-axis. And then RC small, which doesn't have organized convection, is the box plots with out filled inside. And then RC large with organized convection has the filled inside, and it's to the right of the RC small simulations. And then the cloud feedback component, total amount, altitude, or cloud optical depth is defined at the top of these plots. So starting with RCE small, kind of our baseline expectation of what the cloud feedbacks will look like in RCE. Starting with our most simple cloud feedback is cloud altitude feedback. We understand how this what this cloud feedback will be due to our understanding and confidence in how clouds change in altitude with warming SST. And we found that in RCE small, we have this small positive cloud altitude feedback due to the long wave component of this. And this is associated with that proportionally lower emission temperature due to the rising cloud tops and the decrease in OLR. So it's a very confident, all the models follow the same, and the spread across the models is constrained. And then our cloud amount feedback, there's large cancellation between long wave and short wave across all the models. So in the net, it's 0, and it doesn't contribute a lot to the net total cloud feedback. But these signs are associated with decreases in cloud amount, but you can see the variability across RCE is starting to increase across the 0 line. So we do have differing signs, and this is due to differences in the increase versus decrease, kind of pulled by a couple outliers. But primarily in the model mean, we have this decrease in cloud amount, which agrees with the past couple decades of the understanding of how at least free tropospheric clouds change with warming SST and RCE simulations. And then our most complicated cloud feedback is going to be the cloud optical depth feedback, and we're going to see this over and over again throughout the rest of this talk. But we see that it's marginally negative due to the long wave component, and this is associated with decreases in cloud optical depth. It's got our largest magnitudes as well as our largest spread across RCE, and this is going to be mirrored in RCE large as well, where convection organizes. So adding all those up plus the residual term, we have a very small total cloud feedback. It's around 0.14, which is about 4 times less than what we see in the CMIP models. But you can see there's a lot of spread there. Moving into how organized convection impacts these cloud feedbacks. Generally, the cloud feedbacks have stronger magnitudes and a lot more spread across the models. But at least with our cloud altitude feedback, it's still largely positive. There's just one model that behaves a little differently, and it's dominated by that long wave component. One feature that stands out is that the cloud amount feedback is no longer canceling completely. We now have this slight positive component in the net controlled by the short wave features of this cloud feedback. And then similar with the cloud optical depth feedback, the sign of the net component is opposite, and that's being driven by the short wave component. So the importance of the short wave, at least when convection organizes, starts to become more and more important, especially in the cloud optical depth component of this feedback. And then lastly, we're looking at the degree of organization and how it affects the cloud feedback. So we're going to be looking at is that metric of organization on the x-axis as the organization increases, as the x-axis increases. And then the cloud feedback is going to be on the y-axis. The red boxes denote a statistically significant relationship between the cloud feedback and organization. And so what I'm showing here in the top left is the total cloud feedback, the net component, and we see this strong relationship that if a domain has more organized convection, the cloud feedback actually becomes less negative and starts to become positive, which is really interesting. And so we broke apart this cloud feedback and we looked at the different components between the flux components and amount, altitude, cloud optical depth. And we also looked at boundary layer clouds, which is going to be labeled as low 680. So it's cloud top pressure greater than 680 hectopascals. And then we also have our free troposphere clouds, which is high 680. To see what kind of clouds are changing in a different way to make this relationship occur for domains with more organized convection. Yeah, convection. So starting with the shortwave component, because that's the component that's driving the sign of the total cloud feedback, we see this equally strong relationship occur. And so we're like, okay, great, we can continue looking at this. This is primarily coming from the cloud optical depth component in the free troposphere clouds and the cloud amount component in the boundary layer clouds. So for the boundary layer clouds, the cloud amount is increasing instead of decreasing with warming for the more strongly organized domains. And we showed, not shown here, but we show that this is because there's a larger baseline cloud amount in the more organized domains. And so not only do the low clouds increase, but the the cloud amount at 295 is greater in the more organized domains than the cloud amount at 295 in the less organized domains. And then for cloud optical depth, now the cloud optical depth is increasing as opposed to decreasing with SST in these free tropospheric clouds. And this is primarily due to a preferential shift in the distribution of cloud amount in the ISKIP histogram, where as cloud amount is decreasing in these upper clouds, they're decreasing more from the thin clouds. And so our clouds in general are thicker. And then the relationships are similar in the long wave, but of course the sign is flipped. But the primary relationships that we're seeing in the long wave component of the cloud feedback are coming from these boundary layer cloud amount feedback and then the free troposphere long wave cloud optical depth feedback. So finally, yeah. All right. So then the final part of this paper, we compared the cloud feedbacks in RCE to the specific decomposition that Sherwood et al. In 2020, Zink et al. 2022 did to see where RCE kind of compares to these more realistic cloud feedbacks. And so we're just going to look at the total cloud feedback because I want to point out that we found that the model mean in RCE large right here is within the spread of these other studies, but with this substantial amount of spread within RCE large. And we show in this paper, which hopefully will be coming out in the next couple months, that a lot of this spread is dominated by that shortwave cloud optical depth feedback, but that is also an important component to making RCE large behave more similarly to the GCMs and the observations than RCE small. And another part of that is that RCE large actually has low clouds as opposed to RCE small, which does not have low clouds. So I'll leave up my summary. Thank you, Andrew, for inviting me. And are we taking questions? I forget.
Yes, but first we're clapping because thank you for a great talk.
Welcome back.
There's still snow in St. Croix.
Yeah, that's not surprising.
Sorry, Brandon, I've muted you. But yes, thanks, Catherine, for that talk. If anyone has questions, we have a few minutes now. If you want to unmute themselves and ask anything, we'll also loop back towards the end of the session as well. We can have some broader discussion. I think, unless I'm going to cut someone off, I had a question very quickly, which was just, so you showed in one of your panels, there's like for the low clouds, there's a long wave, there's a substantial long wave cloud feedback coming from low clouds. And or is it, oh, okay. So this panel in the bottom left, this low 680 long wave amount. Okay, so it's there, but it's not very strong.
It's very marginal, yeah.
Yeah, okay, that makes more sense. I read it with one fewer zeros than should be there in my head. So okay. Cool.
No, and that's a big thing. The low cloud feedback is there. It's just not strong, but it is several orders of magnitude stronger than RCE small. So there's another part to the study that we did that kind of expands on the relative contribution of low clouds to the all cloud feedback in RCE large. But it requires a lot of setup.
Yes, yeah. Jonah, do you want to ask your question? Do you want to unmute? And
Sure. Maybe I hope I'm understanding it right, but I'm just curious. It looks like here you're looking at how cloud feedbacks depend on the aggregation of the sort of the base state of the initial state, and I'm wondering if you also looked at change in aggregation and saw if that was related at all to the cloud feedbacks. Thank you.
Yeah, so this organization metric that we're showing here is for the average organization across the 3 SSTs in RCE MIP. We did look at the change in organization from 295 to 305 Kelvin. And there is basically, I think, no significant correlations, at least in the method that we used here. And a lot of that has to do with organization itself doesn't really have a concrete in RCE MIP specific change that it does. But we weren't able to show that how organization changes with SST, how it impacts cloud feedbacks.
Fair enough. Thank you.
go on, Shia. You can.
Yeah, just to type my question. Just curious why you don't get low clouds in your RCE small simulations, if I understand correctly.
Yeah, that's a feature of RCE that's pretty consistent. A lot of it has to do with the way the simulation is set up, and then by my understanding, the parameterizations that are still left over in so cloud resolving models, for example, you can explicitly resolve convection, but there are still parameterizations in the microphysical level that occur that are important for these boundary layer characteristics that are highly affect how RCE produces low clouds. It's a little above me, but it is a consistent feature that low clouds in RCE are not necessarily simulated correctly, especially in the small domain.
Cool. How are we doing for time? I have one more question. I'll allow myself one more question. So in RCE MIP, there's like a fixed ozone profile, fixed in pressure for all of the runs. Does that affect when you're thinking about high clouds and high cloud changes? Do you have to, is that something that you have to worry about? And maybe when comparing against the CMIP models or something, or?
That is not something that we thought through, but I do think that is a curious question. But yeah, when considering everything that we looked at here, we did not consider the effects that, at least when comparing to CMIP models, how those different characteristics of the simulation setup would affect what we see.
Okay. We also have another question just came in from Dennis, which I can read out, or Dennis, you can unmute if you want.
Okay, can you hear me?
Yeah, we can hear you.
So I'm looking at the page here, and the trends that are seen are across an ensemble of models. So my question is, do we know really that it's the organization that's causing the differences in the feedbacks, or some other unrelated differences among these models that are causing these differences?
That is a good question. And it could very well be other features of these models. But here we just kind of looked at what the changes in the differences in the organization, at least the metric. But yeah, I wouldn't discount that there are potentially other features based off of the differences in the type of models. But something I think RCMIP, at least whenever we analyze these models, we try to rely on that at least the simulation is configured the same way. And there are consistencies within the models that occur despite their internal differences. So I don't know if that answers your question.
No, thanks. That was a good try.
Great. Thanks again, Catherine. I think we should probably move on to Brett now.
Thanks, Catherine. Our next speaker is Brett McKim, a PhD student at the University of Exeter. And we talk about Anvil Cloud area feedback. Okay, Brett, take it away. Brett, you're muted.
Okay. Can you guys hear me now?
Yes.
Okay, great. All right, thanks for having me today. This talk is about constraining the area feedback of Anvil clouds, and this work was done with my collaborators, Sandrine Bonny, Jean-Louis Dufresne, and Marion Sanlu. And let's get into it. So you've probably seen this plot many times on the ECS Symposium. It's the assessed cloud feedbacks from this comprehensive report a couple years ago. And I just wanted to comment on what are the uncertainties and what are the most uncertain cloud feedbacks. And a lot of attention has been devoted to these low clouds in the past 10 or 20 years. But we've actually seen some recent progress on constraining these feedbacks. Whereas the Anvil Cloud area feedback, this feedback has a lot of uncertainty with it. And well, what's interesting, I think, is how there has been less attention maybe devoted to it in the last 10 or 20 years than the low cloud feedbacks, for instance. So just to look at this problem historically, people have been talking about Anvil Cloud area feedbacks for a long time. There's this paper by Ramanathan and Bill Collins in the 90s that argued for a potential area feedback, and it was later shown that they weren't quite thinking about the cloud feedbacks in the right way. And the evidence they used wasn't really evidence of an area feedback. And then later on in the early 2000s, Richard Lindzen proposed area feedback. And there they showed changes in area that was due to microphysical mechanisms. Well, they didn't really have a precise mechanism. But anyway, there was sort of a strong debates around this topic in the early 2000s. And then you didn't really hear anything about area feedbacks of Anvil clouds for a while. And this stands in contrast to like the lots of research being done on the height feedback and the fixed Anvil temperatures and all this stuff. So anyway, that's just an interesting sort of history to keep in mind. But anyway, this Anvil cloud area feedback, it's a little bit of a misnomer because it's actually due to the changes of two things in Anvil clouds, this area change and this optical depth change. And so the question is, where does the uncertainty come from in this assessment? Is it from purely area changes, or is it from optical depth changes? And so that's what we're trying to resolve in this study. And so to really try to constrain the feedbacks, we're going to try to use a little different approach than what's typically done. We're going to try to use the storyline approach. And this comes from constraining the climate sensitivity literature. where to constrain a bound on climate sensitivity, for a particular bound on the sensitivity to hold, it must be consistent with all the lines of evidence. But we just apply this type of thinking to individual cloud feedbacks. So what that means is right now we're going to consider the area feedback. So let's imagine this. And let's imagine that the area feedback is solely, just due to area changes. Right now, let's be ignorant and just say, okay, only area changes are under consideration right now. How likely is it to produce this uncertainty? So, for example, if we look at the lower bound, this minus 0.4 watts per meter squared per Kelvin, if this requires a large change in cloud area, but that if you go look to the theory and you look to observations and you find that the actual change in cloud area is much smaller, then you can rule out that bound on the area feedback. So to really implement this approach, you need a way to relate cloud changes, something you can observe or predict from theory, and cloud feedback. And so the way that we try to overcome this challenge is with a simple model of clouds and their radiative effects. So we do things like we approximate high clouds as with black body emission, and it's proportional to their area fraction. And then on the shortwave side, we can come up with simple expressions for how they reflect the incoming solar radiation, and then you can come up with expressions for cloud overlap effects. So basically, we've idealized clouds into two distinct layers, high clouds and low clouds. And when you do this, you can actually write down these simple expressions for the TOA energy balance. And these are in terms of bulk parameters that you can diagnose from observations. So, for example, here's Calypso cloud fraction data from 2006 to 2016 or so. You can combine that with the clear sky radiation from series data, and then use our simple model to try to predict what the anvil cloud, with the total cloud radiative effect should be. And so on the top, we have the observed cloud radiative effect. So I have the net in the top, the short wave in the middle, and the long wave on the bottom. And then in the bottom set of three, we have the modeled cloud radiative effects from this really simple two-layer model. So this is a really simple model, but we're able to capture the patterns across the tropics in both the short wave and the long wave. And it only required 3 tunable parameters to do this, which was the high cloud and low cloud albedos, and sort of a cloud thickness parameter. But anyway, you can take these expressions for the TOA energy balance and actually take the derivative with respect to surface temperature. And what you get are analytic expressions for cloud feedbacks. So here I'm showing the high cloud area feedback. So this is solely the feedback due to changes in area, not changes in optical depth. That's considered in a separate feedback, but we'll talk later. So the insight from this simple formula is that your area feedback is proportional to 2 things. It's the present day, on the right-hand side, the present day anvil cloud radiative effect plus an overlap term from overlap with low clouds. And then the fractional change in anvil area with warming. And so that means we can look at the present day cloud radiative effect in observations and then use that to help constrain what the area feedback should be. So I'll show it maybe in one slide, what we do. If we're only considering the tropics, then we should multiply this expression by 1/2 when we extrapolate to the globe for the global average. And let's say we want to look at how plausible this lower bound on the area feedback is. So this minus 0.4 watts per meter squared per Kelvin. If you look to the observations and you look at the inferred anvil cloud radiative effect plus this overlap term, we get something that's very close to 0, so minus 1.5 watts per meter squared. And there's always this question of how small is small? How small is a small cloud radiative effect? Well, if you plug in the numbers and ask, what is the required change in cloud area to produce this lower bound on the feedback, you find that it's actually about 50% per Kelvin. So this is a huge, well, it's a huge change in cloud area. But we should see what the observations say the cloud area change should be, and maybe from simple theory. So if we actually go to look at the observations in interannual variability in the high cloud fraction. So here I basically reproduced a plot from Marion's stability iris paper in 2020, where they looked at the tropical mean cloud fraction and then plotted against the tropical mean surface temperature, and they looked at this year after year. What they found is that you get these changes in anvil cloud area of about -7 to 11% per Kelvin. And if you also take the stability iris theory, which says that your anvil cloud area should be in some sense proportional to the upper tropospheric stability, then you get something closer to -1 to -4% per Kelvin. But the punchline is that both of these are much smaller than the 50% per Kelvin needed to make this lower bound on the area feedback. And so the conclusion we can take away from this is that the area feedback is not that large. And if you plug in sort of a best estimate of the anvil cloud area changes that you get from variability and from theory, your area feedback's very close to 0. It's -0.02, plus or minus a few. And so this is way smaller than the anvil cloud area feedback that you saw in the Sherwood paper. So then let's go back to the optical depth component of the feedback and ask, can we constrain this using the same techniques? And so what I've done here, so here's the shortwave component, because changes in optical depth will manifest in part as changes in the cloud albedo. And so here you see that the feedback depends on this fractional change in the cloud albedo, the high cloud albedo, multiplied by the present day anvil cloud shortwave radiative effect. And so when you plug in the numbers of these shortwave radiative effects to achieve sort of this central estimate of the albedo feedback, if we imagine this being -0.2 watts per meter squared, you only need a 1 to 2% change in albedo to satisfy this. And so the question is, how plausible is a 1 to 2% Kelvin change in albedo? And so if you look to the observations, so this cloudy albedo is our tuned parameter, with one of our tuning parameters in this simple model. And if you tune it every year, you can get a cloud albedo that varies from year to year. And what you see is that you get some increases with warming and then a huge increase during the El Nino. It's not really clear why we get this large change in albedo during an El Nino. But it seems to suggest that these changes in albedo might be plausible. But this should be contrasted with other people who's found that anvil clouds actually thin with warming. So there's a bit of discrepancy between maybe the methodology and what result you get. And it's important to note that an albedo feedback would at least be partially canceled by a long wave emissivity feedback, which we haven't quantified. So the takeaway from all of this is that observations in theory, when you combine them with a simple model, they can bound uncertainties in cloud feedbacks. The anvil cloud area feedback is constrained to be small because the present day cloud radiative effect is small, and we understand area changes well enough to be able to bound this feedback. On the other hand, the optical depth feedback seems to be more unconstrained, both theoretically and observationally. And so this presents an obstacle for bounding Earth's climate sensitivity. So you can check out these results in a preprint available online. This will soon be in print at Nature Geoscience. And I think another great paper to read alongside this is a paper by Adam Sokol and Dennis Hartman looking at anvil cloud thinning in the RCEMIP framework. So yeah, thanks for listening to my talk.
Thanks, Brett. That was great. It
Thanks.
looks like Nature Geoscience is going to be full to the brim with some good stuff soon. Cool. Yeah. So people know the drill. If you have questions, feel free to just unmute yourself or raise your hand. After a few minutes, maybe we'll turn to some more broader discussion. Oh, Mark, do you want to unmute yourself or?
Sure. Can you hear me?
Yep.
Yeah. Thanks, Brett. That was really nice. Just curious why the stability iris prediction is so off. It's off by factor of 2 or maybe even more than that in the response. Is that because you're looking at interannual variability?
I think that's part of it. There's only one model that's really looked at interannual changes in anvil cloud fraction versus the long-term response, and that's this paper by Marion. It's the 2022 paper she has. And there they find that the long-term anvil cloud decrease is about half that of what you find in interannual variability. Now, as like the physical explanation for why that might be, I think that the surface warming from an El Nino might not be so well correlated with the upper tropospheric stability. And so that might cause this mismatch between surface warming, stability, and therefore cloud fraction. So the cloud fraction changes you infer might be different for interannual variability because of this sort of a decoupling between the two.
Yeah, thanks. I seem to recall in Marion's work that the stability iris was perhaps more applicable to certain cloud types, like the thinner distribution as opposed to the thicker distribution. Maybe the actual definition of cloud fraction is, the result would be sensitive to how exactly you're defining your cloud fraction.
Mm-hmm. Yeah, there is some dependency there. And I think in this case, we're really focusing on the precise changes in anvil cloud areas. So like, the fractional change and really quantifying that. And it was a little harder to tell in Marion's paper. Like she found that there were still strong correlations between different optical depth ranges of the high clouds they considered, but it didn't really say what the actual stability the actual cloud fraction change was in those instances. So yeah, there's still correlation, but there's it wasn't so clear if the amount was the same in all of those optical depth bins that they considered.
Thanks.
Mm-hmm.
Dennis says, nice plug for our paper.
Mm-hmm.
Go for it, Jonah. I won't let you get away without saying it.
That's right. I just I don't know if the thing is a technical thing, but I just noticed that you had the cloud overlap term played a role in determining the strength of the area feedback. I mean, also in the optical depth. And I just very naively I would have thought that would weaken the strength of the feedback, but it seems like maybe it increases it. Can you talk a little bit about that term and maybe just sign conventions I didn't
Yeah,
follow?
sure. So the overlap effect, I don't have an equation for it here, unfortunately, but it's basically this term that's proportional to the cloud fraction of the high clouds times the cloud fraction of the low clouds. And in general, this is going to be small. I mean, you can see here on the left-hand side, at least climatologically, high clouds and low clouds aren't really overlapping so much. So that's one reason why this overlap term it comes out to like 0.5 watt per meter squared. So that's in comparison to the anvil cloud radiative effect, which is like -1 or -2 watts per meter squared. So it's actually slightly, kind of comparable. But that's because the anvil cloud radiative effect is so small itself. So in fact, it does act to reduce the area feedback because, in this case, because it's positive, and which just means that when you have low clouds, when you reduce your area of your high clouds, there's going to be some additional area that low clouds beneath them that will get reflected. So it sort of quantifies this effect. So that's how it can decrease the magnitude of the feedback. I don't know if that, design conventions, it gets a little confusing. So it's best just to, I think, look at the equations in the paper to get.
That makes sense.
Yeah, but the net result is it's a small influence. So.
Cool. Okay, thank you.
Mm-hmm.
If people are going to be quiet, then I'll ask them. Oh wait, I'll ask
Mark Zelinka asked a question in the chat that sounded interesting.
I think that was the one that he asked when he unmuted himself, I think. Is that right, Mark? Okay. Yep, he's good. Okay. One thing I was going to ask quickly is, is there anything special about so could you apply this to like CMIP models or to RC-EMIP or something? I'm thinking about the connections between your talk and Catherine's talk, and it feels like so one of the nice things in your work is it's almost like presenting it's like a new decomposition of cloud feedbacks, basically, that's different from these kernel approaches. And it's kind of difficult to know how to compare them without doing without doing the same, just applying it to the same data. Is there an issue with that technically, or is it just a matter of
So there will be some difficulties in comparing to sort of the kernel approaches. So here's the expressions for other cloud feedbacks. So you can do this for low clouds as well, and you can also look at the temperature. So I'm calling it a temperature feedback for anvil clouds and for low clouds, because temperature is sort of the natural coordinate we work with. And so there will be some difficulties comparing to RC-EMIP and CMIP, mainly because of the decomposition they use. So what I mean by that is the reference response. So we're using fixed relative humidity as our reference response rather than a fixed specific humidity. And also we use a fixed anvil temperature as part of our reference response, which is, I might be wrong, but I don't think that's what they do in typical kernel decompositions. So the only paper I know who also uses a fixed anvil temperature as part of the reference response is this paper by Yoshimori. It came out in like 2020. And they were arguing that this could be a more natural way to talk about anvil cloud feedbacks. So that will make it a little bit harder to compare this reference feedback and the temperature feedback to the feedbacks you see in the literature. So this temperature feedback will not give you the same as the anvil height feedback. But I think the area feedbacks should be the same. And between the two, because that doesn't, I don't think that matters whether your reference response has fixed anvil temperature as part of the reference response or not. So the area feedback should be comparable. And I think also the optical depth, but like the temperature feedback would not be comparable to the height feedback. Does that makes sense? Yeah. So they can be compared in principle, but it's just the way we choose to decompose things makes it harder. So
yeah, different reference, like base states or reference states.
It's the same deal why you can't compare feedbacks that have a fixed relative humidity as a state variable versus specific humidity as a state variable. So it's the same sort of deal there. And actually,
I
it would
will
be really
try.
nice to compare the two, our models, like our framework versus what you actually see in models. So, yeah.
Right, I will chime in and say that we did look at like compared your area feedback, and it is similar, if not the same, as the radiative kernel method. And then we also flirted with attempting to do your decomposition and applying it to RCMIT, but I ran out of time. I didn't want to be in a PhD forever. But we were intrigued by your method and we're curious as to whether, like, if we stepped through these approaches using RCMIP data, whether it will result in the same thing or not. But we did show, like, to ourselves that the cloud area feedback was the same and was easily applicable using the radiative kernel method.
Yeah, something that I would need to add to make a better comparison would be include the long wave emissivity. Because right now I'd sort of just assumed that the anvil clouds were optically thick, well, and the low clouds. And so putting in emissivities in them would help to, it would give us a long wave emissivity feedback, and then we could compute like the optical depth feedback that Catherine was showing in her slides.
And just for reference, so what in this set of equations here, what is like which one you mentioned? You alluded to there being 3 tunable parameters. Which ones are the ones you tune?
Yeah, so it's a little hard to see here, but it's so this alpha I that's the high cloud and low cloud albedo. So that's 2 of the 3, and then the third one is one that so because I'm idealizing clouds into 2 layers, it's helpful to plot what I'm doing, like for one example profile. So here's like a profile of cloud fraction in the warm pool, and you see that anvil clouds don't exist at just one level. They have some height structure to them. So what you have to do is collapse that onto one single level, and you have sort of an effective cloud fraction. And so the difference between the peak in this profile and this dot here on the right, further to the right, there is a scaling factor that we've applied. And so this scaling parameter is basically, we used it to tune the long wave energy balance in the, we tune to the observations. And that's how we determined the effective anvil cloud fraction. So that's the third one. Yeah.
And that's
then low clouds
that's the
don't get
quantity
one of
that's
these.
doing. Oh
Yeah.
yeah. But that's the
Because
quantity
they're
that's doing
already
this
quite
weird thing
localized.
in the El Nino. That's the FH that's acting weirdly in the El Nino.
Yeah, so it's the albedos that act sort of weirdly.
Oh, it's the albedo, sorry. Yeah.
Yeah. So the cloud fraction seems to be very coherent, but then this one, there's a huge jump during the El Nino. You also see this, I have the low cloud albedos too. And you also, I mean, this is a kind of these are busy plots, but you also see a big jump in the low cloud albedo during the El Nino. And so I'm not really sure what's going on there. I don't know if it's, I'd be interested to see what's the reasoning behind this, so. And actually, since we have time, I'll just say, like, I think you could use these equations to help diagnose things like intermodal spread. So, for instance, the area feedback, you can have different feedbacks because 2 reasons, at least in this model. It's because their present day cloud radiative effects are different, so their climatology is different. Or you can have differences in their area changes with warming. So you can have biases from both the mean state and the change with warming. So in fact, these equations show how feedbacks are sort of state dependent. So that's another way to interpret the intermodal spread. You could use this to help sort of decompose. Is it because of their climatology is different, or is it because of their change with warming that they're different?
That's very cool.
Yeah.
We've still got a few more minutes left if people have more questions for Catherine or for Brett, or just broader discussion points they want to raise. We're spoilt for time today, so we can discuss things more broadly if people like.
So I have a question. So it seems like if we add all these feedback together, can we get the exact total cloud feedback?
I would hope so, but we haven't checked this. Yeah, so go ahead.
Yeah, so I feel like this kind of a linearization, right, over individual terms, but maybe like individual feedback also depend on others, right? Like they could depend on each other, probably.
Yeah, so I guess they could depend on each other, and that's also true in models. And also, again, like that might be hard to sum up these feedbacks because, like, even here, this reference feedback is this clear sky feedback times a sort of a high cloud masking factor. So clouds influence the clear sky feedbacks even when clouds aren't changing. So that's another example of this state dependency. And I think Bjorn Stevens has a paper where he discusses this in a bit more detail. So it's hard to compare when you have different decompositions. So, but yeah, this is just a linearization. So and it idealizes clouds into 2 layers. So there's probably things where we might miss.
Okay, I see. Thank you.
I mean, it might be interesting just to talk about the anvil cloud area feedback in this assessment. I mean, it's just interesting to talk about like the history of the area feedback. Like I noticed, I don't think it was assessed in the AR4 and AR5. And maybe there's people in the audience who could comment on this, who were could answer why this feedback, we were talking about area feedbacks for a while, and then we weren't talking about them for a while, and then now it seems like we're talking about them again. So I don't know if anyone wants to take that or has anything to say about it.
I mean, so the paper that they based it on was that Ray's paper?
Yeah, Ian Williams, I think, and Ray. Yeah, it was based mostly on this paper, but I guess it's because they were just looking at observational studies and
yeah. But in that paper, they don't explicitly talk about the area feedback, do they? Or it's like inferred from some results in that paper.
Yeah. So you have to do some calculations to take their CRE changes that they compute in their study, and you somehow have to convert these CRE changes into an area feedback. So you have to be careful in how you do that, because CRE changes can change because of clear sky influences, which I think they addressed in the paper. But then to go from that number to the area feedback estimate, you had to do a couple other you had to sort of subtract off the height contribution to CRE changes, the anvil cloud height contribution. So in the, this is a long paper, this WCRP estimate, so they didn't go into all the details. But I think that's how they did it, to get at that number. So that might also be why there was the large error bars, because one study and lots of steps there was a lot of processing to get there.
Great.
Yeah.
I think
If there's
maybe
oh,
go for it, Jonah.
I just ask one. I'm just curious about. I mean, it feels like part of your conclusions are that because the optical depth is hard, doesn't put as much of a constraint on it, that it's harder to speak really about a true bound. I don't want to make you talk about stuff that you might just be beginnings of thoughts, but do you have ideas about how to properly constrain this, or what
Yeah,
dealing with this?
I think it will help to consider the long wave component. So there's going to be a cancellation with the long wave. And so that in itself will make it easier to constrain. And then I'm also starting to think about some of Adam Sokol's work. So let me just go back to, there they think about anvil clouds as this continuum between thick and thin. And I think that can help to, I think if you combine my work with sort of the simple model of CRE, but you look at it from this, in this coordinate system where you distinguish between thick anvil clouds and thin anvil clouds, I think you can combine that to make a constraint that better than what we did in this work. So that's sort of work I'm beginning now, and that's just my hunch that this will be the way to go forward. But I'm sure there's going to be challenges with this, but we'll see.
Sounds really intriguing. Looking forward.
Yeah, and that's why I recommend reading both the papers. I hope they're in the same issue. So yeah.
Great stuff. Yeah, let's thank Catherine and Brett again. Two fantastic talks, two very exciting scientists. And yeah, we'll be back next month with a debate or a panel discussion with Rob Wills and Peter Huybers. So yeah, see you next time. Thanks, guys.
Thanks, everyone.